In 2018, I got to walk across the surface of a receding glacier in Iceland. From where I stood, I could see a patch of snow and ice off in the distance, the last remnants of another glacier that had since melted away. That ice-speckled area was all that remained of 800-year-old Ökjökull, or Oak Glacier, which was officially declared dead in 2014 by Icelandic geologist Oddur Sigurdsson. It once spanned an area as large as 38 square kilometers. In 2019, the loss of Ökjökull was commemorated with a plaque on the site of the former glacier. It's the first monument dedicated to a glacier lost to human-induced global warming. Looking after our planet and all its dynamic ecosystems and landscapes, including glaciers, is everyone's job. We know rising temperatures are correlated with rising carbon dioxide in the atmosphere, and the amount of carbon dioxide generated by our day-to-day actions can have an effect on the other side of the world. But while individual actions matter, who is emitting carbon dioxide is highly unequal. About half of total US emissions in 2019 were direct emissions from corporations, coming from sources like power plants and oil and gas production facilities. So they also have responsibility to share the burden. Knowing who or what is emitting carbon dioxide is only part of understanding climate change. We also study who emissions affect and the geographical impacts of a warming planet. Climates are complex, so I don't have all the answers, but there's a lot we can learn. I'm Alize Carrere, and this is Crash Course Geography. Even with a problem as complicated as climate change, we can start with a picture. Like this picture of Muir Glacier in Alaska from 2004. Pictures and maps can show us where land masses, oceans, and geographical features are located, which is spatial information that we kind of take for granted. The Earth is dynamic, and we have to remember that both pictures and maps are really snapshots of a particular time. So if we compared this image to past ones of the same area, we'd see how it's changed, and we could explore why change is happening here. A photo taken in 1941 from the exact same spot as the recent photo shows an entirely different landscape. The glacier was much bigger. After looking at lots of old and new photographs, current glaciological surveys, and the geologic record, we know glaciers around the world in places like Alaska, the Swiss Alps, and Mount Kilimanjaro have shrunk dramatically. Muir Glacier is just one example. To get deeper into the why, we know that ice and snow melt faster as air temperatures get warmer. But glaciers also depend on how much precipitation they get each year. If less snow accumulates, glaciers lose more ice on their bottom edge than they can replace at the top. That precipitation comes from the hydrosphere, and its regional patterns can depend on temperature and wind patterns over distant oceans. So mountain landscapes have changed as climate patterns have changed, which ties back to the global energy budget and insulation and the beginning of the Earth. It's a complicated problem. The terms climate change and global warming are often used interchangeably. But even though these phenomena are closely related, there is a difference between them. Climate change is the change in average weather patterns in a region over a long period of time. These changes can be natural or anthropogenic, meaning human-induced. And when I say long, I mean each climate period can last for several decades or longer. For example, there was a little ice age that happened from 1300 to 1850 CE. Mountain glaciers expanded worldwide, and mean annual temperatures dropped by 0.6 degrees Celsius in the northern hemisphere. That's a 550-year climate pattern, which then changed to a different one. On the other hand, global warming is the increase in the average surface temperature of our planet. In our current period of global warming, there's been a well-documented rise of average temperatures around the globe since the Industrial Revolution in the 1700s and 1800s. So when scientists or leaders talk about global warming, they're almost exclusively referring to this recent warming, which comes from human activities that increase greenhouse gas emissions, like carbon dioxide, methane, and nitrous oxide. They trap solar energy, so more heat is held in the atmosphere. That additional energy is changing not only the average temperature, but also climate processes within the atmosphere and oceans. These include more extreme storms, heat waves, droughts, changing regional temperature and precipitation patterns that cause vegetation zones to shift and glaciers to melt, which results in sea level rise and changing coastlines. Essentially, when the planet gets warmer, climates change. We know the Earth has had many different climates thanks to paleoclimatologists, who study past climates through proxy data, or data that provides clues about the past. Comparing multiple proxies gives us a more complete picture of what happened and helps us anticipate the changes we need to prepare for. For example, they use tree rings that show dry and wet years, fossilized bugs that tell us about moisture and temperature levels of bygone ecosystems, or deep-sea sedimentary records that reveal the ocean's past. Like the deep-sea sedimentary record shows that the Earth overall had one of two extreme climates, and glaciers advanced and retreated across the Earth at least 28 times during the past 2.6 million years. We can see that when glaciers advance and the climate is colder, glaciation occurs and sea levels drop. And when the climate is warmer, glaciers retreat and sea levels rise, ushering in an interglacial period, which is what we're in right now. One of the most useful kinds of proxy data for atmospheric conditions and how climates changed year to year are ice core data. From ice, we can extract the chemical composition of past atmospheres. Using special drills, paleoclimatologists have extracted long tubes of ice from ice sheets and alpine glaciers all over the world, and estimated climates going back at least 400,000 years. Let's go to the thought bubble. On the top is fresh snow that fell this year and the year before and the year before that. Underneath is the snow that fell when Marco Polo traveled the Silk Road, and beneath that, when the Buddha gained enlightenment. And the deepest layers were laid down long before recorded history. The very bottom of ice sheets in places like Greenland and Antarctica have snow that fell before the beginning of the last ice age, 115,000 years ago or more. Just like snow on a sidewalk can get compressed by boots into sheets of slippery ice, the snow on ice sheets is compacted into huge solid masses. And buried in each layer of ice is evidence of past atmospheric conditions. Tiny air bubbles, which act like time capsules. Once an ice core is moved from the field to the lab, scientists use isotope dating to tell whether the carbon dioxide in those frozen bubbles was released from burning materials like wood or coal in the lithosphere, or if it was airborne during a nuclear explosion, or if it was part of the natural cycling of carbon. Paleoclimatologists have collected polar ice core samples and analyzed historical air bubbles from Greenland and Antarctica, tropical glaciers in the mountains of the Andes and Kenya, and mid-latitude glaciers in the Alps and Himalayas. When all these data are lined up, scientists can compare them with each other and see atmospheric trends, which in turn shows climate change over thousands of years. Analysis shows that it can take just a few decades to change from colder to warmer climate patterns. That might not sound fast, but when you're a 4.5 billion-year-old planet like the Earth, that's nothing. Thanks, Thought Bubble. By analyzing proxy data like bubbles and ice cores, we know the Earth's climate has changed significantly many times. As geographers, let's go deeper into why these drastic changes happen. Based on that proxy data, paleoclimatologists hypothesize that climates change because of any combination of several driving forces. First, past climates could have changed because of orbital causes, like changes in the shape of the Earth's orbit, its tilt on its axis, and the time of year when the sun is closest to the Earth. Like calculations by the mathematician Milutin Milankovitch show that lots of glacial cycles occur every million years. Second, volcanic activity can release enormous amounts of volcanic dust into the stratosphere. Strong winds spread that dust around the world, darken the skies, and reduce the amount of insolation that can reach the surface, which lowers temperatures. This is related to the albedo effect, or the amount of sunlight a surface reflects back into space. Volcanic dust and even the color of surfaces change Earth's albedo. White surfaces, like ice, reflect the sun's energy, creating a cooling effect. So when there's less ice, the opposite happens. Darker surfaces absorb sunlight and warm the surface of the Earth. Similarly, when something big like an asteroid strikes, it can cause an impact winter. Like volcanic activity, a big impact throws dust and debris into the air, blocking out insolation and lowering temperatures. Such an impact may have caused the extinction of the dinosaurs 65 million years ago. Another reason that climates change is when continents and oceans get rearranged. Like when the Isthmus of Panama formed, it broke the connection between the Atlantic and Pacific Oceans, which redirected ocean circulation and created the Gulf Stream. This changed how moisture and ocean currents moved around the globe, which, as we know, contributes to climate patterns. And finally, climates change when greenhouse gases in the atmosphere change. We know from ice core data that carbon dioxide levels in the atmosphere decreased when glaciers formed during ice ages and increased during interglacial periods. However, what's happening now is unlike anything in the past. We're in an interglacial period now, and glaciers are melting faster than ever before in the geologic record. Average annual global temperatures have risen between 0.3 degrees Celsius and 0.6 degrees Celsius, and sea level has risen between 10 and 25 centimeters during the past 100 years. And in 2016, global atmospheric carbon dioxide levels passed the 400 parts per million mark, which is higher than at any time in the past million years. More carbon dioxide increases the amount of heat trapped in the lower atmosphere, enhancing the natural greenhouse effect that makes life possible. So our climates are entering new patterns. If this upward trend in global temperatures was caused by natural processes alone, geographers would consider it natural climate change. But like I said, what's happening now is unlike anything we've ever seen on Earth. So scientists have used multiple lines of evidence like tree ring and ice core data, glacial retreat and sea level rise, isotope dating, changes in atmosphere, and changes in weather phenomena to study the climate. And they've concluded that there is a greater than 95% probability that human activities, like burning fossil fuels, industrialization, modern agriculture, and deforestation, have caused most of the Earth's warming since the mid-20th century. We are experiencing anthropogenic global warming. But not all areas will be affected equally by global warming and modern climate change. While materially rich countries are the main producers of greenhouse gas emissions, Materially poorer countries will bear most of the impacts, like becoming climate refugees, people being forced to flee their homes for safer places. Thousands of low-lying islands and coastal cities face a threat of rising sea levels by the end of the 21st century, when sea levels are predicted to have risen 26 to 77 centimeters. That's pretty significant considering over half of the world's people live within 100 kilometers of a coastline. For example, located halfway between Australia and Hawaii, Kiribati has 33 atolls that sit less than 2 meters above sea level and average only a few hundred meters wide. The government of Kiribati is planning a two-phase migration with dignity and has purchased several thousand acres of land in Fiji as a potential resettlement location for its 102,000 residents. But migration with dignity isn't an option for all countries and communities. For some places, adaptation is the only option, like building seawalls or raising streets and homes. And for some, that will mean moving to higher elevations after the flooding without government support for the process. Flooding from sea level rise is just one of many changes that we can anticipate. Other places, for example, will experience drier conditions with the potential for droughts, heat waves, and wildfires. The current ways the Earth's climate is changing because of global warming will affect all of us as individuals, so it's our collective responsibility to pay attention and take action. Here's the thing about human-induced climate change. Knowing that we humans are the main cause means it's also in our power to try and stop it. We still have a small window of time to work together and aggressively reduce our emissions to save communities around the world from disaster. To do that, our individual choices can make a difference, but we also have to hold corporations and governments responsible for the policies and large-scale emissions that affect our atmosphere and climate. This will ensure safer, healthier, and more biodiverse futures for the next generation who inherit our planet. I know the problem of global warming may sound overwhelming. You're not alone. But from decades of science, we know what the problem is and what the solutions are. It's now just about finding ways to successfully integrate them into society. In future episodes, we'll continue to examine how geography can help us work on the problems that pop up where climate change intersects with society. This has been the focus of my research for the last several years, and even though it's an urgent area of work, it's also incredibly motivating and exciting to be a part of finding the solutions. Many maps and borders represent modern geopolitical divisions that have often been decided without the consultation, permission, or recognition of the land's original inhabitants. Many geographical place names also don't reflect the indigenous or aboriginal people's languages. So we at Crash Course want to acknowledge these people's traditional and ongoing relationship with that land and all the physical and human geographical elements of it. We encourage you to learn more about the history of the place you call home through resources like nativeland.ca and by engaging with your local indigenous and aboriginal nations through the websites and resources they provide.